what's your answer here? So what's your answer here? Let's say, for example, we want your radius to be equal to the outside radius. You have now this one to be T R all over T. We have 300 bar or 30 megapascal. So this one is a 300 Newton per millimeter squared. What about your outside radius? That will be 25 plus twice the thickness. So that will be 35 millimeters, yes? The outside radius. Outside radius will be, I'm talking about the diameter. So R will be equal to 25 plus 5, right? Sorry. So that will be 25 plus 5. So that will be in millimeters. Sorry, we're talking about the radius. And then your thickness here is 5 millimeter. Okay? So if you try to look at this one here, this one will simply cancel out the millimeters, so you're still left with Newton per millimeter squared or still megapascal. So what's your value here? 30 divided by 5, that's 6. 6 times 300 is 1,800 Newton per millimeter squared, or this one will be megapascal. Well, of course, you have now this one here, sigma ZZ, to be PR all over twice the thickness. So this one now is simply sigma theta theta divided by 2. This one now is 900. How about that? And what about the next one? What about your shear stress? So this one is PR all over J. What is your torque? 1.2 kilonewton meter. Let's have a look. 1.2 kilonewton meter that's 1,200 Newton meter. And your outside radius is 30 millimeter. So be consistent with the unit here. You have meter there, you have millimeter here. So most likely you have to multiply this one with 1,000 to convert this meter to millimeter. What is your polar moment of inertia? Yes? So as you can see, this one is a meter, and this one is millimeter, and this one is millimeter to the fourth. So meter, if you have this one millimeter squared, this one will be millimeter to the fourth. You can cancel out 2 here, cancel the meter, Newton per millimeter squared, that is a megapascal. So you have to be consistent with your units here. This one will be 1,000 millimeter per meter. Cancel that. So once you cancel that, this one is millimeter squared already. So this one is millimeter squared. So your units here will be Newton per millimeter squared or megapascal. Yes? So this one is 1,200 kilonewton, 1.2 kilonewton meter. So that's 1,200 Newton meter. Yes? So you can get this value. What's this value? Sorry? 54.65 megapascal. Okay. So as you can see, okay, we have sigma theta theta, sigma z z, and we have a small twisting shear twisting stress here, or the shear stress. So as you can see, this one is still dominant. This one. Sigma theta theta, what should be the value? Oh, okay. So that's 180 and 90, is it? Okay, thank you. Now, if you want now to write your state of stress, so let's assume now everything is now okay. So this one is 180, that's 90, 54.65, 54.65. So that will be a megapascal. How about that? Yes? And of course, since this one is 2D, it's very easy to calculate for your principal stresses. It's quite straightforward. You simply take the determinant of this one, and that you will be able to get the principal stress. What I mean to say is that you have this one here, 180 minus sigma, or of course you can use the equation that we have, not a problem. So take the determinant of this one. If you haven't memorized the equation or you don't have it with you, it's not available. So take the determinant of this one, equate to 0. So if you try to look at it, you will have a quadratic equation wherein you will have two roots. So that's 180 minus sigma, 90 minus sigma, minus 54.65 squared, that is 0. So you'll end up to have a quadratic equation here, and the roots of your equation will be sigma 1 and sigma 2. So once you have sigma 1 and sigma 2, calculating the von Mises stress is not anymore a problem. Is that okay? Or if you want to, the alternative is, of course, you have sigma squared minus I1 sigma plus I2, that is equal to 0. So this is, if you have the equation available with you and you want to use it, you can simply use that. Or if it's not readily available and you forgot, then you can simply take the determinant of this one, equate it to 0. Both are correct. You'll end up to have the same values or principal stresses. Any questions so far for this one? So continue with the next problem. So I want want you to be familiar with the theory of elasticity and pressure vessels before we move on to plasticity. By the way, I still have a lot of makeup to makeup lessons, so I wonder if you're available on Thursday morning. Thursday morning, starting this week. Is it okay? 10 to, let's do it 10 to 12. Is that okay? 10 to 12, and then let's have another one in the afternoon. I would like to take the opportunity because your lab, what's this one, microelectronics lab will still happen on week 7, so I probably have to do it as early as possible so that you can at least be confident with mechanics of solids and structures. So let's have it Thursday. Let's start Thursday, 10 to 12. This coming Thursday. Oh, sorry. Will you be addressed by Professor John Marsh? There will be a visit by Professor John Marsh, the dean or the head of the school head for engineering, Glasgow. Is there any meeting? No, but you have seen him already, I suppose. Yeah. Okay. So, okay, let's have it then 10 to 12. So please work on this one here. Next meeting, I want to start with plasticity. So work on number 5 and let's see what happens. So we also have, in addition to that, you need to solve for this one. Please discuss. You have the right equations for this one.